Hi everyone, this is Mrs. GA, and today we are going to learn about the binomial theorem. The binomial theorem will help us with what's called binomial expansion, which is really just multiplying out binomials such as x plus 1 squared, x plus 1 cubed, so on and so forth. So you can do all of these expansions by hand, right? You can sit there and to do x plus y to the power 5, you can do x plus y times x plus y times x plus y 5 times. It will take you a while, and there's a lot of terms to combine and a lot of chance to make a mistake. Or we can learn to use what's called binomial expansion. So it helps us do this multiplication but much quicker and a lot easier. So the first thing that we need to learn about before we even start talking about binomial expansion is called Pascal's triangle. So Pascal's triangle is this pattern of numbers. It makes a triangle. So the top number always starts with 1, and in Pascal's triangle we actually call this row 0. And then in each consecutive row, you can find the term of the triangles by adding up the two numbers that are diagonally above that spot. So if I look at this spot here, if I add up this number and nothing, it gives us 1. And here if I add up 1 and nothing, it gives us 1. And again, this is row 1. And then if you look at this next row, this spot you're just doing 1. In this spot you're adding up 1 and 1, which gives us 2. And in this spot you just have 1. So that's row 2 of Pascal's triangle. And so on and so forth. So all the outer terms are always going to be 1. But if you look at this term, 3 comes from 1 plus 2. Same for this number, the 2 plus 1. For these terms, 3 plus 1, 3 plus 3, 3 plus 1. And you can continue as many rows of Pascal's triangle as you want. So these numbers in Pascal's triangle actually show up with binomial expansions. And if you're expanding out a basic binomial like x plus y, the numbers of Pascal's triangle are going to be the coefficients of the terms in your expansion. So you'll notice that to raise a binomial to the power of 3, we can look at the numbers from row 3 of Pascal's triangle, 1, 3, 3, 1, and we see that they're actually the coefficients of the terms in our answers. So these numbers from Pascal's triangle are going to be a really big part of this binomial expansion that we're going to be doing today. Before we talk about the rest of the binomial theorem, now of course we can draw out our own Pascal's triangle, and we can pretty quickly make quite a few rows, but there is a way to find specific terms within any row of Pascal's triangle, and it's by using a combination formula. So a combination formula, it is a formula that looks like this. So two different ways that commonly you see these written. You'll see like a sub n and then a capital C and then a sub r. We can read this n choose r, but again it stands for a combination, which is a concept we'll cover more when we talk about probability. But it has a formula. So it's n factorial over r factorial times n minus r factorial. And a factorial is really just multiplying. Let me show you an example. So like for 5 factorial, it's just 5 times 4 times 3 times 2 times 1. So you're just multiplying all of the successive whole numbers all the way down to 1. So there is a formula for this, and again that's for n choose r, or you might sometimes see it written like this with 2 large parentheses and then n on top and r on the bottom. So you can use the formula, or your calculator can actually do combinations. It's going to be really important that you know how to do that in your calculator. But this combination formula can actually help us find each of those terms from Pascal's triangle. So the first number, this n, is going to be the row of Pascal's triangle, remembering that we always start with row 0. That top is really just row 0. And then r is just going to be the relative position of the term also starting at 0. So we would call this like the 0th term, and this would be the first term. So here r is 0, here r is 1. Or here r is 0, r is 1, r is 2, r is 3. So again, we can find specific values from Pascal's triangle using a combination. And of course, Pascal's triangle does not stop at the 5th row. It can continue infinitely. All right, so now that we know all about Pascal's triangle and then how it's going to tie into this binomial theorem, we can actually look at the binomial theorem. So this is really kind of like a formula for a binomial expansion. So say we have the binomial expansion a plus b to the power of n. So let's look at each term and see if we can interpret what is going on here. So you can see the first thing is that coefficient, which is just the term from Pascal's triangle here. And this is always going to start with n choose 0, because remember that first term we call r 0, and then we have n choose 1, n choose 2, and then that's going to continue until it eventually becomes n choose n. Okay, so whatever power this is, eventually you will reach that power here, or that number here. Okay, so you can see this first part is just the term from Pascal's triangle. The next thing you'll see is that we have our powers of a, which is the first part of our binomial. So here we have a to the n, a to the n minus 1, a to the n minus 2, and then it continues on for however long it needs to, and then eventually we end up with a to the power of 1, and then a to the power of 0. So what does this mean? This just means that the exponents for your first term are descending. So it's going to start with n, or whatever power you're raising your binomial to, and then each term after it, it's just going to decrease by 1 until it eventually turns to 0, meaning you don't see that term at all, because anything to the power of 0 is 1. So far, here's what we see. That NCR, that is the term from, or let's say the value from Pascal's triangle. And then what else do we see? We can see that the exponents for a are descending. So again, they go from n all the way down to 0. And now let's look at the next, or the last part of each term, which is that b term. So you see that we have b to the power of 0, b to the power of 1, b squared, dot, 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 b to the power of n minus 1, and then finally b to the power of n. So what does that mean? Well, it means that the exponents for your b term are increasing. So they start with 0, meaning you don't see the b term in the first term of your expansion, and they increase until they eventually reach n, which is the overall degree of the expansion. So the exponents for b are increasing. So essentially, you have to find the term from the terms from Pascal's triangle to give you that coefficient, and then you take whatever the first part of your binomial is, and those exponents will decrease as you move down, and you take the term from the second part of your binomial, and those exponents will increase as you go down. Okay, so you can follow this general pattern to help you expand any binomial. Now, it is also possible to find a specific term of a binomial using this formula right here. So this is kind of a general formula for any term of an expansion. So it's n choose r times a to the power of n minus r times b to the power of r. Now, if you look at the terms here, right, here's n and here's r. This number always matches this number, and this number is always n minus r. So if this number is 2, this is n minus 2. So just remember that when you're doing this, n is the degree of the expansion. So whatever this number is here, whatever you're raising your binomial to the power of, and r is the relative position in line, remembering that we start with 0. So we would call this the 0th spot in line, the first spot in line, the second spot in line, so on and so forth. So again, you can use this if you just want a specific term of a binomial rather than the full expansion. All right, so let's give one of these a try. So we're going to be using the binomial theorem to expand this out. So we're not going to sit here and actually multiply it out 5 times. We will expand it using the formula we just learned. So the first thing I'm going to do is I'm going to look at this n, and I'm going to also look at row 5 from Pascal's triangle, and I'm going to list out the values that we see. So the values from Pascal's triangle for row 5 are 1, 5, 10, 10, 5, and 1. Okay, so those again are just from Pascal's triangle, row 5. Then we're going to take the first part of our binomial, which in this case is x, and we're going to start by raising it to the power of n, which in this case is 5. And then for each successive term, it's just going to decrease by 1. And then in our last term, it's just x to the 0. I'll show it out, but you don't have to because that will just simplify to 1, so we won't actually see the x. And then we take our second term in our binomial, which in this case is -2. We do need to be careful with the negative. And we're going to start by raising it to the power of 0, and then that will increase with each successive term. So it's a -2 to the power of 1, -2 squared, -2 cubed, -2 to the 4th, and -2 to the power of 5, which is our n value. And then we're just going to add all of those terms. Then the last thing we do need to do is simplify. So here we have 1x to the 5th times -2 to the power of 0. That's just x to the 5th. But here we have 5 times -2 here, so this term actually becomes -10 x to the 4th. And then this next term, we have 10 times +4, so we have 40 x cubed. And then here we have 10 times -8, so -80 x squared. And then here we have 5 times +16, so that gives us +80, and then that's just x. And then the last one is just 1 times -2 to the power of 5, which is -32. And then the x we don't see because x to the power of 0 is just 1. So this is our final expanded binomial. So you'll see that those terms that we have from Pascal's triangle don't always end up in our final answer because sometimes we're actually going to be multiplying them by a value. But they are going to be the coefficients in this first step of expanding out our binomial. So again, you start with Pascal's triangle values from row 5 in this case, and then your first term decreases in power and your second term increases in power, and from there it's just a matter of simplifying each term. All right, so at this time, go ahead and pause the video and see if you can give this one a try using Pascal's triangle and the binomial theorem. All right, go ahead and check your work here. So one thing, maybe a pattern that you notice between the last example and this example, is that for your final answer for your expanded binomial, the number of terms in your answer is always going to be one more than the degree of your binomial. So this one was 4, and we actually end up with 5 terms. And if you looked at the last example, we're raising it to the power of 5, and we end up with 6 terms. Okay, let's try another one together. So same idea, this one just takes a little bit more to simplify. So let's start by writing out the terms from row 6 of Pascal's triangle. So we have 1, 6, 15, 20, 15, 6, 1. And then we're going to take our first term, which is 2x, and that's just going to start decreasing. So 2x to the 6th, 2x to the 5th. And notice I'm putting 2x in parentheses, so I remember to raise both the 2 and the x to the power of 6. 2x to the power of 4, 2x cubed, 2x squared, 2x to the power of 1, and then 2x to the power of 0. And then we're going to do the exact reverse for that second term, which is 4. So 4 to the power of 0, and that's going to increase. So 4 to the power of 1, 4 to the power of 2, 4 cubed, 4 to the power of 4, 4 to the power of 5, and 4 to the power of 6. And my terms got a little bit squished here, so I'll put those plus signs in between. I never seem to leave quite enough space. And now, again, it's just a matter of simplifying. So let's start with this first one. If you raise 2 and x to the power of 6, you get 64 x to the 6th. And then for the next term, you have to do 2 to the power of 5, and then also multiply that by 6 and then 4. And we get 768 times x to the power of 5. So I'm going to take a moment and finish multiplying the rest out. Hold on one second. All right, here are the rest of the terms multiplied out. So again, from here, it's just a matter of just cubing or raising each term to the correct exponent and then multiplying all of the values together. Okay, so for these, some of your numbers can get pretty large and it can get a little messy, so that's why it's really important that you show your steps and you just take your time when you're simplifying your expansion. Okay, so go ahead and pause the video and see if you can try one of these on your own, and we will check your answers in just a few moments. Okay, go ahead and check your answers here. One thing to notice here, because that second term is negative, the signs of your answer are actually alternating, because when it's raised to an even degree or 0, the whole term stays positive, but when it's raised to an odd degree, it actually turns our whole term negative. So we have that alternating sign pattern. Okay, so now we're going to practice finding a specific term in our expanded form. And for this, we can use that general formula that we talked about, which was n choose r times a to the power of n minus r times b to the power of r, where a is just your first term in the binomial and b is the second term. And remember, r is the relative position, assuming that you're starting at 0. So when you're finding the fourth term in line, that's actually going to be when r is 3, because it's the 0, 1, 2, 3. So the fourth term is actually when r is 3. And since the expansion is to the power of 7, we know that n is 7. And then in this case, a is x, that first term, and b is negative 2. So once you've found these, you're really just plugging it into this formula here. So we're going to do 7 choose 3 times x to the power of 7 minus 3 times negative 2 to the power of 3. And then 7 choose 3, we could either use that formula that we learned for combinations, or your calculator can actually do this. If you're using the TI-30X calculator, you can look for a button on your calculator. It looks like this. It says PRB. If you click that and then you scroll over one, there's an option that says NC, see R. It looks just like our combination. So to do this, you actually have to type in the number 7 first, and then you hit that button and select and choose R, and then you could hit 3. And then when you hit enter, it should tell you 35. So your calculator can calculate combinations for you. And then this is x to the power of 4, and then negative 2 cubed is negative 27. So then we just need to finish simplifying this by multiplying our values, and here's what we get. And one thing I do want to point out, I don't want you to assume that because it's the fourth term, that's how we got x to the power of 4. That's only the case here just because the n value is 7, but it's not always the case that if you're finding the fourth term, it's going to be x to the power of 4. That was kind of a coincidence for this problem. Okay, so just remember that r is the relative position in line, assuming that we start at 0. So if you want to find the fourth term, it's actually when r is equal to 3. Okay, go ahead and try this one on your own. Pause the video, and we will check our answers in just a few moments. All right, go ahead and check here. So in this case, since it's the third term, r is 2. In this case, n is 5. Our a value is 2x, and b is 2y. So you just plug it into our formula and simplify through. And again, this is another one where it's just a coincidence that it's the third term and the answer is x cubed. Again, that's just happens to be because the n value is 5 and r is 2 in this case. And then also just make sure as you're going through these problems that, for something like this, that you're actually cubing the 2 and the variable for both of these. All right, this is the last one we're going to try together. So here we're going to find the term with x cubed in this expansion. So we have to do a little bit of critical thinking here. So if we want to find the term with x cubed, we know that the first term, when we multiply it out, will have x to the 5th, and then the next term will have x to the 4th, and then the third term will have x cubed. So it's the third term when we list it out, but that means that our r value is actually 2, because when we're doing this, we assume this is when r is 0, then r is 1, then r is 2. And then the rest is just plugging it into our formula. We know that n is 5, our a value is 3x, and our b value is negative 4. So we're going to do 5 choose 2 times 3x to the power of 5 minus 2 times negative 4 to the power of 2. And then 5 choose 2, we know from the previous example, is 10. And then this becomes 27x cubed. And then this becomes positive 16. And then it's just multiplying those values together. So we get 4,320 x cubed. So again, it's the same idea. We're still using that same formula as the last two examples. It's just a different way of wording it. Instead of saying, oh, find the third term, we're saying find the term with x cubed. All right, and then here is our last example for this video. So please pause the video and give it a try. All right, go ahead and check here. So in this case, the term with x squared is actually the 7th term, because you have x to the 8th, x to the 7th, x to the 6th, x to the 5th, x to the 4th, x cubed, and then x squared. So it's the 7th term in your expansion, which means that r is 6. So remember, r is always 1 less than the relative position, really. And then n is 8. You can see here, and a is x, and b is negative 1. So you just plug it in and simplify it, and you should get 28x squared. All right, so that is all for today's lesson. Thank you so much for watching.